This is the second video of our specific multivariable distribution examples, and this is the bivariate normal. So two continuous random variables. The last video was discrete. They were the multinomial, which is a discrete distribution. Two continuous random variables x and y are said to be jointly normal, or to follow a bivariate normal distribution if their joint probability density function is, ouch, this. So let's take a look at this monster here. It actually isn't as bad as, ooh, that's not what I wanted. It's not as bad as you might think. If we sort of take a look at it piece by piece, it's not as insane as you might think. So first of all, if you remember the density function for a a single variable normal, we have this. We had sigma sub x times root 2 pi and e to the minus 1/2 x minus mu over sigma sub x all squared. So if we accept this one as being familiar now, almost delightful, one might think, if you can recognize this one, then the joint one is not that far off. So first of all, what happens outside? We have 2 pi, not root 2 pi. We have both standard deviations, right? And then we have this extra little term here, which is related to, that is our rho. That is the correlation between x and y. So we have minus 1/2 again, and then also the little something with the correlation. Here you've got the same term that you would for x, right? There's the same term, x minus mu over sigma squared. There's the same term, but for y, they are added together, and then this cross term, which kind of makes us think of the variance formula a little bit, or the squaring out, right? It looks, this is not that bad if you think sort of x minus y squared, right, is x squared plus y squared minus 2xy. Well, it's kind of similar to that. Yeah, not exactly the same, right? But it's not as outlandish as one might think. So the support for this is the entire xy plane, as all of r squared. And the parameters, the mu sub x, mu sub y can be any real number. The sigma sub x and sigma sub y have to be greater than 0, and rho has to be between minus 1 and 1. Now, these things are named so that we interpret them as the means, the standard deviation, and the correlation, but that is not necessarily true just because they're named that way. That actually would require some work to show that, but they are named that way because that does in fact come out to be true. So if we were to graph this thing, when we talk about the bell curve, right? Well, the bell curve is a single curve. This is actually a bell surface, and it is a three-dimensional bell. It's a three-dimensional bell. So this is one example of what that density function would look like graphed in R3. So probabilities would be volumes under that, but integrating this, right, I can just hear the gasps of horror that you're thinking, well, I have to integrate this. No, you won't. Just like integrating the normal is very difficult, if not impossible, with simple tools, then integrating this is also not something that you will need to do. but that is the volumes and under that surface, those are probabilities. But what we are going to do is use some results of this, some results that make things a little bit more manageable. And so I'm not going to prove any of these results. Some of them are within our grasp. They're just a little tricky to do, and we're just going to accept that they are true for the moment. First of all, the marginals, right? The marginals for x and for y. If you were to integrate out y and you got f sub x, or you were to integrate out x and you got f sub y, you would find that those match the density functions for a normal variable. So f sub x is a normal random variable with mean mu sub x and standard deviation sigma sub x. And y is a normal random variable with the appropriate mean and standard deviation as well. So that's really quite nice. That's really quite nice that the marginals both are normal with the appropriate parameters. Rho does turn out to be the correlation of those two variables, right? If you were to do the integral to find it out, you would find that rho is the correlation. And there's an extra result here, which is, we need to be careful, not true in general. It has something special here for the bivariate normal. X and y are independent if and only if rho is 0. Our normal direction is x and y are independent, tells us that rho is 0, but not the other way around, right? The other way around is not true in general. For the bivariate normal, for jointly normal variables, it is true in both the directions. Uncorrelated and independent for jointly normal are equivalent. They are equivalent. Next, linear combinations. All of this good stuff, all that we've talked about so far. If we have a linear combination of jointly normal variables for any a and b and r, any linear combination, then that linear combination w will be normal. It will also be normal with parameters, well, parameters that are calculated using the usual properties, right? The properties of the expected value would give you this. This would give you this for the expected value of w, a mu sub x plus b mu sub y. The properties of variance, right? The properties of variance where you had a squared times v of x plus b squared times v of y plus 2ab covariance of xy. Those are the usual properties. They have been applied here, and you get this with the extra little bit of care that is taken that the covariance, right, the correlation was the covariance over the two standard deviations. So if we need the covariance, those standard deviations have been multiplied up. So these results here, these results are just the usual results with those parameters applied. Now, let's just be a little bit careful with our implications here with normality and linear combinations. What I have just said is if x and y are jointly normal, if they are jointly normal, then any linear combination of them is normal. That is what I have just said. What we have seen previously is if they are independent normals, then any linear combination of them is normal as well. What is not true, and you need to be careful in your assumptions about normality and linear combinations. If I were just to say that x and y are normal, which means that they might be dependent, and I did not say they were jointly normal, then a linear combination might not be normal, right? That assertion here without the words jointly and without the words independent is false, So we need to be careful about our assumptions about normality and linear combinations. And then We have just finished talking about conditional probabilities. You will be excited to learn, I think, that the conditional densities here are also normal. It's like normality for everybody. If x and y are jointly normal, then it's normality all around. You remember that a conditional distribution was like restricting to a certain value. So if I look at this one, y given that x is equal to x0, well, if x is equal to x0, then that is like the plane, x is equal to x0 intersecting the surface, and you can kind of just see it. You can kind of see it right here, that the curve that you get with that intersection looks like a bell curve. I mean, that's not a proof. That's just sort of a visual justification that this is something reasonable. Now, the issue is those parameters. Ooh, baby. Oh, those are complicated. So the mean of this conditional is, well, you can read it here, mu sub u plus rho times sigma sub y times x0. Don't forget x0 is that constant. x0 minus mu over sigma sub x. And the standard deviation, 1 minus rho squared, the square root of that, times sigma sub y. Analogous thing for the other conditional, for the other way around. Right, so everything has changed. It's perfectly symmetric here. You can read what those are. They are toothsome, right? They are big and you can really sink your teeth into them, but they are not difficult in this in as much as that we are then just talking about normal single variable normal distributions now. So let us go and look at this example, which explore some of these concepts. So let x and y be jointly normal random variables with parameters mu sub x, sigma squared sub x, mu sub y, sigma squared sub y, and rho, right? Rho is non-zero, so they are not independent. In fact, right, a simpler way of saying that is they are dependent. They are jointly distributed, jointly normal, dependent random variables. So let us find the probability that 2x plus y is less than 3. Since they are jointly normal, any linear combination, so here they've used v instead of w, any linear combination is normal. So what do we have to do? We have to figure out what the mu is. Well, that's using the properties of the expectation. You plug in those values from above and you're going to get 2. We have to figure out what the standard deviation is, right? The variance is our standard deviation squared. So we have to figure out that. There is your property of variance from before, applying these values with the fact that the covariance is the product of the standard deviations times the correlation. Again, you plug in all those values from above and you will get 12. And so the variance, the linear combination v is, normally we would give that with the square root, which they do put in here. So the probability that we are looking for, this guy was called v, is less than or equal to 3 is, well, that is just how you would do a normal. It is a single variable normal, and so you're using the standard normal table, right? You're using the z, the standard normal table, to find that probability. And once you've got it down to this, right, then it is familiar. Then it is completely familiar. B. Find the covariance of x plus y and 2x minus y. So notice here, this is the same property that we had before. If you want the covariance given the standard deviations and the correlation, well, you just multiply them, right? The covariance over the two standard deviations gives you the correlation. So you multiply those guys up. And again, plugging in the values from up here, if you multiply these together, you will get 1. And then this is also a property that we've seen before. Remember, it's like multiplying x and x, so 2 times the covariance of xx, which is the variance of x. Here, minus the covariance of xy, plus 2 times the covariance of yx, which you will remember is the same thing as xy, and then minus the covariance of yy, plugging in those values above, and you get minus 1. And then using our property 4 was the property of the conditionals. So what was the question? That's the question. C, find the probability that y is greater than 1 given that x is 2. So we are going to apply this formula here to find the distribution of y, given that our little x0 is 2. And so we're going to use these massive formulas here to calculate the mean and the standard deviation. So here is the mean, there is the formula from in there, and if you plug in those values, you will just get 1. Here is the variance, and so here is that's the formula from above. Again, you plug those in and you get 3, and therefore we have a normal distribution with the mu is equal to 1 and the sigma is equal to root 3. And so that probability, once you know what your distribution is, right, you are just doing a single variable calculation, right, the complement, so that we have greater than, not less than, and you find that you get actually 50%. So the multivariate normal, I'm not going to say more about it than this. We just talked about the bivariate normal, 2 variables. Multivariate normal with more than 2 variables. If you thought the formulas were complicated here, the situation with joint normality is even more complicated, and we're going to leave it there with the mere suggestion to you that it is possible for more than 2 variables to be jointly normal as well.